At 1:23:40 a.m., an operator presses the AZ-5 emergency shutdown button, the system designed to stop a nuclear reaction. Seconds later, power surges beyond control. Fuel ruptures. Steam pressure tears through the core. An explosion rips the reactor building apart. A second blast follows. The roof is gone. The core is open to the night air. Firefighters climb onto the roof, unaware they are standing on radioactive fragments of the reactor itself. Inside the control room, no one believes the reactor has exploded, so the first response is not evacuation, it is investigation. Men are sent back inside. By morning, dozens have absorbed lethal doses of radiation. Within a year, plant managers and engineers stand trial. They are convicted. The verdict is clear. Operator, error. Case closed. But the button they pressed was designed to make the reactor safer. So why did it make everything worse? We're going back to the start of the chain, because what happened in those seconds was the trigger, not the cause. If you value investigations that go beyond official verdicts, subscribe, because this story does not end in the courtroom. Chernobyl Nuclear Power Plant stood in northern Ukraine, near the city of Pripyat. It had 4 nuclear reactors, supplying electricity to millions of homes across the Soviet Union. On the night of April 25th, into the early hours of April 26, 1986, Reactor 4 was scheduled to undergo a safety test. The purpose of the test was to determine whether, in the event of a sudden external power loss, the turbine's momentum could continue generating electricity for just under a minute, long enough to keep the cooling pumps running until the emergency diesel generator started. Earlier that day, operators began lowering the reactor's power in preparation for the test. But the regional grid operator requested a delay as electricity demand remained high, and the shutdown was postponed for several hours. The test was pushed into the night shift, leaving a less experienced control room crew to carry it out. As power was reduced, Xenon-135 began accumulating inside the fuel. Because xenon absorbs neutrons, which are the particles that sustain the nuclear chain reaction, the growing concentration of xenon suppressed reactivity and drove power lower than intended. At one point, reactor power collapsed to near zero, far below the level planned for the test. Operators responded by withdrawing more control rods than regulations allowed, stripping away much of the reactor's built-in safety margin. Control rods absorb neutrons and regulate the nuclear reaction. Inserting them reduces power. Withdrawing them increases it. By the time the test resumed, most of the control rods had already been withdrawn. In addition, several automatic shutdown systems were disabled because they would have stopped the reactor and canceled the experiment. The emergency core cooling system had also been partially disabled as part of the test configuration. Each step taken to keep the test alive stripped away protection. By 1 a.m., Reactor 4 was operating at low power, with most control rods withdrawn and key safety systems disabled. At 1:23:04 a.m. on April 26th, the test began. Steam to the turbine was cut to simulate a loss of external power. As the turbine slowed, cooling water flow through the core decreased. With less water-absorbing neutrons, reactivity increased. Power began rising. 36 seconds later, the AZ-5 emergency shutdown system was activated. AZ-5 automatically initiated full insertion of the control rods, the standard emergency procedure designed to halt the reaction. But as the rods entered the core, reactor power spiked instead of falling. The RBMK reactor had a positive void coefficient at low power, meaning that as steam bubbles formed inside the core, reactivity could increase rather than decrease. Under stable conditions, that risk could be managed, but Reactor 4 was not stable. Its control rods were fitted with graphite tips. When inserted, those graphite tips entered the core first, briefly increasing reactivity before the neutron-absorbing sections followed. Full insertion of the control rods took nearly 20 seconds. In the first moments of AZ-5 activation, the shutdown system introduced a surge before it could suppress one. Under those conditions, The emergency shutdown amplified the reaction instead of stopping it. In the seconds that followed, two explosions tore through Reactor 4, blowing apart the core and partially ripping the roof from the building. Within minutes, a fire was burning on what was left of the roof of Reactor 4. The flames had also spread to the roof of Reactor 3 and to the shared ventilation stack between the two reactors. Firefighters arrived quickly. They climbed onto the roofs to extinguish the flames, unaware that highly radioactive graphite and fuel fragments from the reactor core were scattered across the surface. They were standing on pieces of the reactor itself. Inside the control room, the operators had no clear picture of the destruction above them. They knew there had been an explosion and that firefighters were responding to roof fires, but they believed the reactor core remained intact, not destroyed. Radiation measuring devices, called dosimeters, were checked. The highest range dosimeter available could measure up to 3.6 Röntgen per hour. It immediately maxed out. But 3.6 Röntgen per hour was simply the upper limit of the scale. The actual radiation levels near the reactor were thousands of Röntgen per hour, high enough to deliver a lethal dose within minutes. Because the meters could not register anything higher, the scale of the disaster was not immediately understood. Under the assumption that the reactor was still intact, teams were sent deeper into the building. Radiation levels were already far beyond survivable limits. Shift supervisor Alexander Akimov continued directing efforts from the control room, unaware that the core had been destroyed. He would die weeks later from radiation exposure. By sunrise, the first responders were also critically ill. By morning, residents of Pripyat could see the aftermath of the explosion. Smoke rose from the direction of the power plant, and a faint glow lingered above the damaged reactor building. Inside the local hospital, the first patients from the nuclear plant began arriving. They were mainly firefighters and plant workers who had been on the roofs and inside Reactor 4 during the night. Many were already vomiting. Some complained of severe headaches and dizziness. Others reported a metallic taste in their mouths. Skin reddening began to appear within hours. Doctors initially treated them for burns and smoke inhalation, but blood tests revealed rapidly falling white blood cell counts, a clear sign of acute radiation exposure. By late afternoon, the most severe cases were selected for emergency transfer to Moscow, where specialists in radiation medicine were located. Other operators who had been on duty, but were not critically ill, remained at the plant. They were questioned by officials and instructed to provide written accounts of the night's events. That same day, a government commission led by Deputy Prime Minister Boris Sherbina was dispatched to Chernobyl. Control of the response shifted from plant management to the Soviet state. The priority was no longer simply understanding what had happened, it was preventing the situation from escalating further. While hospitals treated the injured, officials confronted a different danger at the plant. The reactor core was open to the air, fuel and graphite were still burning, and there was concern that molten nuclear fuel could burn through the concrete beneath the reactor. If that happened, it could trigger further explosions or contaminate groundwater below the site. Under the direction of the government commission, an emergency plan was approved. Helicopters would drop materials directly into the destroyed reactor. The objective was to smother the fire, absorb neutrons, and reduce further radioactive release. Beginning later that day, repeated missions dropped sand, clay, boron, and lead into the open core. Sand and clay were intended to suppress the fire. Boron absorbs neutrons and was meant to limit nuclear reactivity. Lead was added to help shield radiation. Hundreds of tons were released, but the operation was being carried out without a clear understanding of the core's condition. Some engineers believed parts of the structure remained intact. Others feared the core had been completely destroyed. By the end of the first day, residents of Pripyat had still not been evacuated. Many continued their normal routines, unaware of the level of contamination spreading through the city. Inside the power station, engineers were trying to understand what had happened in the final seconds. In Moscow, an explanation was already forming. That explanation focused on operator violations and loss of control. It was not entirely wrong, but it was incomplete. While officials debated causes, radiation continued to drift across Pripyat. the reactor had exploded in the early hours of April 26th. By the next afternoon, the city was still functioning. Schools open, shops trading, children playing outside. And every hour that passed increased the radiation exposure of the residents. 36 hours after Reactor 4 exploded, the buses arrived in Pripyat. Loudspeakers announced a temporary evacuation. Residents were told to take only essential belongings and that they would return in a few days, but they never did. Apartments were left unlocked. Meals were left on tables. Pets were left behind. Within hours, nearly 50,000 people were gone, but radiation had been spreading through the city for more than a day. And by the time the evacuation began, thousands had already been exposed. The evacuation was underway, but it had come too late. And while Pripyat was emptied, radioactive particles were already moving far beyond the city. And the longer Moscow stayed silent, the more likely it became that someone else would announce the disaster for them. 2 days after the explosion, radiation was detected more than 1,000 kilometers away. On the morning of April 28th, elevated levels were recorded at the Forsmark Nuclear Power Plant in Sweden. At first, staff feared a leak at their own facility. When inspections found nothing wrong, atmospheric analysis traced the contamination back across the Baltic Sea. Radioactive material had crossed international borders, and Moscow had made no public announcement. Only after Swedish officials demanded clarification did the Soviet government issue a brief statement on the evening of April 28th, acknowledging that an accident had occurred at Chernobyl. The announcement gave no meaningful detail about the scale of the explosion or the level of radiation released. In Kiev, May Day celebrations went ahead as planned on May 1st, despite lingering uncertainty about radiation levels. On May 14th, nearly 3 weeks after the explosion, General Secretary of the Communist Party, Mikhail Gorbachev, addressed the Soviet public on national television for the first time in relation to the disaster. He acknowledged the seriousness of the situation after weeks of limited public disclosure while defending the state's response. Inside the Soviet system, the emphasis fell on operator error. That explanation identified responsible individuals, but it did not address the deeper problem: a reactor design that could become unstable at low power, and a shutdown system capable of briefly increasing reactivity. At the time of the disaster, 15 RBMK reactors were operating across the Soviet Union, with more under construction. RBMK was the Soviet graphite-moderated, water-cooled reactor design used across the program, not a one-off machine at Chernobyl. A public admission of a design flaw would not have implicated one shift of operators. It would have raised questions about every RBMK reactor still running. Instead, blaming the men in the control room contained the damage politically. In August 1986, Soviet officials presented their formal account of the accident at an international conference in Vienna under intense global scrutiny. The emphasis remained on procedural violations inside the control room. But outside the Soviet Union, few believed that was the whole story. While officials debated responsibility, the situation at the reactor site remained unstable. Through late April and into May 1986, helicopters continued flying missions over the open reactor, dropping thousands of tons of materials into the ruins. The visible fire diminished. Airborne emissions began to decline. At the same time, the evacuation widened and winds carried much of the radioactive fallout north into Belarus, particularly into the Gomel region, where some of the heaviest contamination would settle. By early May, authorities established a 30-kilometer exclusion zone around the reactor, an area permanently closed due to radioactive contamination. Entire villages within that radius were cleared. By the end of 1986, approximately 116,000 people had been permanently relocated. In the years that followed, an additional 220,000 would be resettled from contaminated regions beyond the original zone. By late May and into June, inspections and internal measurements confirmed that the core had not cracked. It had been torn apart. Fuel and graphite had collapsed into a highly radioactive mass inside the wreckage. In the months that followed, that molten fuel solidified into a lava-like substance, later known as corium. Deep inside the ruins, one mass in particular became infamous, a hardened formation nicknamed the Elephant's Foot. When first discovered, its radiation levels were so extreme that prolonged exposure would have been fatal within minutes. Beneath the reactor, there was a second fear, that the molten nuclear fuel could burn through the concrete slab of the reactor and contaminate groundwater below the site. To reduce that risk, miners were brought in to dig a tunnel beneath Reactor 4. They were told plainly what they were being asked to do, that the heat, the conditions, and the radiation could kill them. Many still agreed. They tunneled beneath Reactor 4 to create space for a concrete and cooling barrier under the core. Within the core, 3 plant workers volunteered to enter flooded corridors beneath the reactor to open drainage valves and reduce the risk of a secondary explosion. Above ground, another problem remained. The explosion had scattered fragments of highly radioactive graphite and fuel across the roofs and ledges surrounding Reactor 4 and above Reactor 3. Before any permanent structure could be built around the reactor, that debris had to be removed. Remote-controlled machines were sent first, but they failed. Radiation disabled electronics within minutes. Vehicles stalled, cameras went dark. No remotely operated system could survive long enough to clear the material. So men were sent instead. The soldiers assigned to the roof were later referred to as bio-robots. Teams ran onto the roof in tightly timed shifts, often less than a minute. They pushed heavy graphite blocks back into the destroyed reactor below and retreated before exceeding their assigned dose. Thousands of these short missions were carried out through September, and by October, the most heavily contaminated debris had been removed from the surrounding roofs. Radiation levels remained extreme, but the site was no longer shedding loose fragments into the environment. Construction works to contain the reactor could now begin in earnest. Through the autumn, working under strict exposure limits and racing against winter, crews assembled a massive steel and concrete enclosure over the remains of Reactor 4. In October, one of the helicopters assisting with construction struck a crane cable and crashed near the reactor, killing its crew. Even months after the explosion, the site remained lethal. But by November 1986, the steel and concrete enclosure, known as the sarcophagus, stood. The reactor was no longer exposed to the open air. Immediate emissions were reduced. The site was stabilized, but at extraordinary human cost. Over the course of the response, more than 600,000 people would be mobilized in cleanup, containment, and decontamination operations. They would later be known collectively as the liquidators. The physical disaster had been contained, but containment did not end the crisis. It changed its form. The question was no longer how to seal a reactor, it was how to explain it. The Soviet leadership needed an account that demonstrated control at home and credibility abroad. It also needed to protect the wider RBMK reactor program. An explanation was being constructed, one that would assign responsibility, but not necessarily accept it. The only question was what it would leave out. By late 1986, the immediate emergency had been contained, but the consequences were only beginning. Western regulators and nuclear agencies treated Chernobyl not simply as a disciplinary failure, but as a warning about reactor design, safety culture, and crisis transparency. International nuclear bodies demanded data, and the RBMK program became a subject of open technical examination rather than quiet internal management. Long-term health studies later documented elevated rates of thyroid cancer in regions exposed to radioactive fallout. At the same time, changes were already underway inside the Soviet nuclear system. Between 1986 and 1988, RBMK reactors across the country were modified. Minimum control rod insertion limits were raised. Additional automatic protection systems were installed to prevent unstable, low-power operation. Control rod designs were altered. Operating procedures were tightened so that the test conditions that existed at Chernobyl could not be recreated in the same way again. The goal was clear: prevent a repeat of the same sequence. In July 1987, more than a year after the explosion, 6 plant officials stood trial for the disaster. Plant Director Viktor Bryukhanov, Chief Engineer Nikolai Fomin, and Deputy Chief Engineer Anatoly Dyatlov were each sentenced to 10 years in a labor camp. Other senior personnel received shorter terms. The court ruled that violations of safety regulations and operating procedures had caused the disaster, a clean verdict with identifiable individuals to blame. But the political consequences extended beyond the courtroom. Within the Soviet Union, pressure for greater transparency intensified. The disaster exposed the limits of information control in a nuclear age. The policy of glasnost, which was launched by Gorbachev and sought increased openness in government and media, expanded rapidly in the years that followed. Chernobyl did not create glasnost, but it accelerated it. No single failure caused Chernobyl. But once the sequence began, no single action could stop it either. It was the interaction between design vulnerability, human decisions, and delayed transparency that made the disaster irreversible. It is possible to tell the story of Chernobyl as total institutional failure, but that would ignore another reality, which is that the disaster did not stabilize on its own. Helicopter crews flew repeated missions over an exposed core to reduce emissions. Engineers improvised monitoring systems inside contaminated structures. When remote-controlled machines failed on the reactor roof, thousands of men cleared radioactive debris by hand so construction could proceed. Under extreme time pressure, a massive concrete and steel shelter was assembled over the destroyed reactor. It was not permanent, it was not elegant, but it reduced ongoing releases and made the site manageable. Below ground, miners tunneled beneath Reactor 4 to facilitate a concrete and cooling barrier to prevent further contamination. Without those interventions, the environmental and human consequences could have been significantly worse. Chernobyl exposed how tightly design, decision-making, and secrecy were intertwined. It also showed how quickly the state could mobilize once the scale became undeniable. The disaster was contained with concrete and manpower, but the consequences couldn't be contained at all. A button designed to make a reactor safer revealed how fragile the system behind it really was. If you enjoy investigations that examine how systems fail and how small decisions become irreversible, consider subscribing for more.